Okay, yeah, maybe you can start. So just let me know if my screen is visible. Yeah, so I'll be speaking on something called matchings and arborescences. So how many of you guys know what a graph is, to start with? Well, better yet, is there anyone who does not know what a graph is? Okay, if everyone knows, then maybe we'll do this. Okay, so uh, okay, since all of you know what a graph is, let me quickly go on to something called matchings. So basically, a matching is a set of edges in a graph such that no two chosen edges touch the same vertex. Like for in this example, you can see that this is a graph on basically four vertices, and then you take the edges AC and BD, and these two edges share no common vertex. You can take other examples like yeah. So in this case, change the color. Could very well be a matching. Let's say these three edges. Yeah, maybe I should add edge here. Also, this set of edges is also a matching. Let me name this vertices A1, A2, A3, V1, V2, V3. So A1, V1, A2, V2, and A3, V3. This set of edges is a matching. Also, A1, V2, V1, A2, and A3, V3. This set is also a matching. So the first thing to note is that a matching might, yeah, so matching might not be unique. There can be quite a few matchings in a given graph. And well, a matching need not cover all of the vertices in the graph. Like, for example, this is a matching, but even just A1, B1, and A2, B2 will also be a matching. So one matching need not be unique, and two matching need not cover. Yeah, so that is a matching. And okay, do you guys know what bipartite graphs are? Or anybody who does not? Okay, good. Since maybe again formally define it, bipartite graph is defined as basically two disjoint sets of vertices x and y, such that the edges only exist from x to y or y to x, whatever. But there are no edges in between two vertices of x. Like for example, if there is x1 and x2 belonging to x, then x1 and x2 cannot have an edge in between. But if there's like all edges should be of the form xi yj. So like this is an example of a bipartite graph. So like what do you try to match normally? Well, many kind like in real world, you can do the like for example in schools you have these clubs and then all the students are required to join a club. Let's say there's a strict mandate that you can join exactly one club. So the left side could be the students, the right side could be the clubs, and then each student joins our club. So it could be one matching. Or maybe if the condition is each students join at most one club, this is a proper matching that student S1 joins club C1, student S2 joins club C3, student S3 chooses not to join any club. But let's say if there's a mandate that you must join a club and you can join exactly one club. In that case, what you need is called a perfect matching. Well, maybe before coming to perfect matching, I'll just define what a complete matching is. That would be easier for you guys to understand. Cool. So coming to the formal definition of what a complete matching is, it's let's say you're given a bipartite graph G, then a matching M being a subset of the edge set, is called complete from X to Y if for all X belongs to X, there exists Y belongs to Y, such that the edge XY belongs to M. And since M is a matching, each vertex of X is incident to exactly one edge of M.
So,
Yep.
so this bipartite graph, can you just explain it once again? Like I can't get it.
So the definition. Oh, is my voice low? Wait, maybe I'll try something. Yeah. So bipartite, the definition of bipartite or the matching part in bipartite? Which one do you want?
Like matching would cover perfect. Like
Oh,
please.
okay. So yeah, let's say consider this. This is a bipartite graph. Like so, this is your partite set X. This is your partite set Y. Both are disjoint sets. This is, let's say, this represents your students and this represents your clubs. You are given a job to assign a student to a club. The students have submitted their preferences of which clubs they might join. Based on their preferences, these edges are assigned. Like S1 only wants to join either of C1 or C2, S2 wants to join either of C2 or C3, S3 wants to join either of C2 or C3. So now, and there can be no edges between students because, well, in the practical scenario, students are not joining students and clubs are not joining clubs. So yeah, so that is the main point of bipartite graphs. It's within this set, there are no edges between the vertices here. And within this set, there are no edges between the vertices here. It's just from one of the sets to the other. So now,
So like in between two sets is bipartite setting.
yeah. So like there are no intra-set edges. Like there is no edge from S1 to S2, S1 to S3, or any
Yeah.
such combination.
Got it.
Yeah. So like what I had said is that if their condition is you need to assign each student at most one club, then this assignment of S1 to C1 and S2 to C3 works fine. But now if you're mandated that every student must be assigned to a club and exactly one club, then just this matching does not suffice. So you need to either send S3 to C2. Okay, there's one more condition is that all the students in the like each student needs to take a unique club. So yeah, moving on from that, let's me define what a complete matching is. Yeah, so complete matching is basically, well, let's keep it simple for the beginning. Let's say you want to have a complete matching for all the vertices in this set X. So you would say that a matching is complete. Well, till now you understand this, that a matching has to be a subset of the edge set, because a matching contains of edges. So uh, a matching is complete with respect to this partite set X if every vertex if every vertex in X is part of exactly one edge belonging to M. The same might not hold true for the vertices in Y. So in this case, you call this matching to be complete from X to Y. But it need not be complete on the entirety of X. Like, you can also define the complete matching to be on just a subset. Like, for example, a matching can be complete on just X1 and X2. In that case, you would just need the edges X1, Y1, comma, X2, Y3 to be your matching. And you have a complete matching on this subset of X, X1 and X2. Oh, yeah. Also, complete matching is like a complete matching from X to Y is also called a matching that saturates X. Technicalities won't be that important. Now coming to a perfect matching. So a perfect matching is one in which every vertex in the graph belongs to exactly one edge. So first is that every vertex in a graph belongs to a edge that okay, I'll start with this. Every vertex in the graph does not belong to more than one edge. That's your matching condition right there. So basically, at most one edge contains each vertex. Now for the perfect matching condition, it needs to be that the vertex, so the differentiation could be, yeah, I'll come to that. Every vertex belongs to exactly one edge. Yeah, so the difference between complete and perfect matching is basically this, that, well, in this case, as you saw, uh, the matching that we took here, let's say x1, y1, x2, y3, and x3, y4. In that case, there was no edge that contained y2 in our matching M. But in this very case, there's exactly one edge that contains every vertex. So that is the basic difference between a complete matching and a perfect matching. A complete matching is with respect to a particular set of vertices that might not be the entire vertex set. Like,
So for
so
perfect matching,
yeah, basically you can say that a perfect matching is a complete matching of X union Y. That is the vertex set.
so sir, this is only possible when both the sets have equal elements.
Yeah. Like if any of the sets has like more than the other set, elements more than the other set, then this is not possible here. Also, yeah, one point. Please don't call me sir. Okay, now coming to, well, a condition that shows you when a matching can be perfect. It's called the Hall's marriage theorem. So let me start with defining what a neighborhood is. So let's forget about the formal definitions. I'll just give you an intuition that works best. Give me a minute. I'll just think about it. Yeah, 100%. Okay. So neighborhood. So let's say this is one of your graphs. You know, some edges here and there. So basically, a neighborhood of a vertex, let's say you consider this vertex, is the set of all of those vertices to which it is connected to by an edge. Like, for example, if this is V1, this is V2, this is V3, then V2 comma V3 forms the neighborhood of V1. Now, if you're considering of a subset of the vertices, then okay, maybe let's take S to be V1 comma V2. Then the neighborhood of S is the neighborhood of V1 union neighborhood of V2. So basically it becomes V2, V3, V4, V1, all of those. So let's write it down. NS becomes your V1, V2, V3, V4. Now, from the definition of bipartite graphs, it should be obvious to you that the neighborhood in bipartite graphs, if you take S to be a subset of X, then NS would strictly be a subset of Y. Does that make sense? Yes. So yeah, if S is a subset of X, then if you are taking the neighborhood of this S, then it should be a subset of Y. Because there cannot be any edges between vertices of X. The vertices of X are strictly connected to the vertices of Y. So for every vertex, let's say X1 in S, it can only be connected to some Yi, Yj, Yk in Y. And those will belong to its neighborhood. No X, let's say L, can belong to the neighborhood of S. So now what Hall-Smadek's theorem states is that there is a matching that saturates X if and only if the cardinality of the neighborhood of S is greater than equals to the cardinality of X.
So saturating X means?
Saturating X means, as I told, that it's basically when there exists a complete matching from X to Y, then when a complete matching exists on X, then you say that it saturates X.
Okay.
Okay. So if there is a matching that saturates X, then we have this if and only if condition that the cardinality of the neighborhood of S has to be greater than equals to the cardinality of S for every subset S of X. And if as someone had pointed out, the cardinality of X and Y, if they are same, then a matching that saturates X is a perfect matching. So let's just do a rough check of this condition. Like, for example, in this case, you'd
had we made it like had we defined it that for a perfect or complete matching, one element in X, so X set will always be matched with exactly one element in set Y.
Sorry, I did not get you. Could you repeat?
Like, is it necessary for a perfect or a complete matching to have exactly one element in set Y to correspond with one element in set X?
Yeah, because what this perfect matching does is basically it connects two like it's a set of edges, right? And each edge can contain at most like okay, each vertex is associated to at most one edge in this, you know, matching. So for each, let's say for xi, there exists an edge. That edge needs to be connected to some yj in the set y. So, and then with the condition that no vertex can be associated with more than one edge. So yj cannot have another edge going to it from this set of edges that belong to the matching. So there is exactly one edge between xi and yj and no other edges. So yeah, there's
So
one, yeah.
one xi will be connected with at most one element in y set.
In a perfect matching, it will be connected to exactly one element in yj.
Okay. So, sir, why is this mod of how can this mod of n of s can greater be s possibly be like it is will always be equal to s, when won't it?
Yeah, it will be equal to s if s is equals to x. But so we are defining the neighborhood not with respect to the edges in the matching, but with the complete set of edges that we have for the graph. So yeah, if s is equals x, then this necessarily has to be this. There is no other option that I have. But let's say if S is a proper subset of X, then this might not hold true. Like I'll show you in an example in a while. Okay, maybe I'll just show where it holds. So yeah, for example, check in this case. So let's say I take S to be x1 comma x2. This is a proper subset of X, where X is my x1, x2, x3. Now the neighborhood of S will be, well, with respect to x1, I have vertices y1 and y2 in its neighborhood. With respect to x2, I have vertices y2 and y3 in its neighborhood. So here the neighborhood of S is strictly greater than the neighborhood of, sorry, the cardinality of the neighborhood is strictly greater than the cardinality of S. So the condition that greater than equals to, yeah, it holds. Yeah, in this case, you can find a perfect matching. I mean, this is a perfect matching, you can see. Now, let's see a case where this condition does not hold. I mean, it should be intuitive still, but I'll show. Well, this condition does not hold, and so the perfect matching never exists. Like, for example, consider this case. Take S to be again x1, x2. Now the neighborhood of S here is just y1. So NS is less than the neighborhood of the cardinality of the neighborhood is less than the cardinality of S. So now you have a problem is that you have to necessarily decide whether to match y1 to x1 or x2. Let's say you choose x1. So you have no vertex that you can match x2 to. And thus you can never get a perfect matching here. Thus the proof should be kind of intuitive. And it should be intuitive why it's a necessary and sufficient condition. Like, for example, if a matching saturates X, then every set S, which is a subset of X, is matched to, you know, distinct vertices in the neighborhood of S. So this must hold true if a perfect matching exists. And if this holds true, then, well, this is kind of a method to go by to get a contradiction that if this holds true and a perfect matching does not exist, then this fact itself is contradicted. Like, for example, start with the largest possible matching that you can get. And you assume that there is no perfect matching there. So even in the largest possible matching, there will be one X naught, say, that will remain unmatched. So like follow an alternating path, like first use an unused edge, then go for a matched edge, and keep on repeating this process. So now let S be the left side vertices that can be reached from X naught. And all the neighbor of S must already be matched back into that is to say, Like for example, here in this case, let's say you are considering that x1 is not matched at the end. So you can reach x2 and x3 from x1 by taking a path, let's say x1, y2, x2, or you can reach x3 via path, x1, y2, x2, y3, x3. And now you will see that each of the vertices in this needs to be matched back to this as set difference x naught, as this says, because if not, then there must be one vertex remaining in y that can be matched back to x naught. But according to our assumption, that is not happening because it's not a perfect matching. So we get a contradiction that the cardinality of ns will be less than equals s minus 1. And thus you will see that this contradicts the Hall's condition, and so a complete matching, or rather a perfect matching, must exist. But now let's come to the interesting part of this. So in matching, now forget about just vertices. Let the vertices have preferences now. Consider these vertices to be humans. So we have two groups or two sets, x and y, of the same size. And each vertex or each person in each of these groups is allowed to rank all the vertices on the other side. One example that people give is student and project pairing, but well, I personally feel like that's not a very good example in the stable matching setting. It's rather a good example in something called a popular matching setting that will come on towards the end of this talk. So a rather very classical example that actually comes in, and where this modified, before this modified name, the name that was originally given to this problem was the stable marriage problem. So yeah, from there, consider this to be a set of boys and this to be a set of girls. Now, each boy has a preference order of all the girls. And mind you, each boy ranks all the girls and each girl ranks all of the boys. Now, what we want is we want to make a perfect matching in which we match boy-girl pairs. And we want this matching to be stable. So what do I mean by stable? Well, I have a picture here. Yeah. So perfect, you understand. What do I mean by stable? So stable means there can be no blocking pair. That is, let's say in the matching that you give, in the perfect matching that you give me, you pair x1 to y2 and x2 to y1. But then you find out that x1 preferred y1 over y2, and yeah, x1 preferred y1 over y2, and y1 preferred x1 over x2. So this is not a stable matching because, I mean, no one's stopping x1 and y1 to form an edge, leaving their current, partners. So in that case, this will be called a blocking pair where, so I mean, in any case, this will be called a blocking pair where a member in both of the parties prefer the partner of the other person over their own partner in that particular setting. Then we call it a blocking pair. And in that case, it's an unstable matching. What we want is the absence of these blocking pairs to get a stable matching. So to do that, Gale and Shapley, they gave an algorithm to deal with this kind of a problem. So one side, that is say X, they make proposals, and the other side, say Y, keeps only their best current proposal and rejects the rest. So the high-level algorithm goes like this, that you start with every vertex being unmatched. And now while there is some X belonging to X that is still unmatched and has not proposed to everyone, X proposes to the highest rank Y belonging to the set Y that it has not proposed to yet. And Y now figures out that, well, if Y is free, is unmatched, then Y forms an edge with X. But if, let's say, Y has an edge with some other, say Y has an edge with XJ, and now XY comes in and proposes. So if Y prefers XJ over XI, it keeps that edge. If Y prefers XI over XJ, then it breaks off the edge with XJ and forms an edge with XI. This process continues unless all of them have been matched, and then all the proposals stop, and the pairs that you have at that point becomes your final perfect stable matching. So yeah, maybe this will be a very boring example, so I'll just show you an kind of an animation. Okay, is this website visible?
Yes, sir, it is.
Yeah, so you start off like this. Okay, maybe I'll just give you a moment to take a look at the preference list. So A1 has this order B1, B2, B3, B4. A2 has B3, B1, B4, B2. A3 has B2, B1, B3, B4. A4 has B4, B2, B3, B1. Same, the group B also has a preference order for the vertices in A. And we choose that B proposes to the vertices in A. So now we start this. So for starters, B1's first choice was A1. B1 proposes to A1. A1 is free. So it accepts and an edge is formed. Now B2 proposes to A3. Again, it was free, it accepts. B3 proposes to A4. It was free, it accepts. Now B4 proposes to A4. Well, maybe I'll go a step back. Yes. So B3 and A4 had formed an edge. Now going back to the preference list. A4, right? Yeah. So in A4's preference orders, B3 comes much later than B4. B3 is its first preference. And B4's first preference is also A4. So B4 goes on to propose A4. Now A4 weighs its option. It had an edge with B3, but B4 is a better option for it. So it breaks the edge with B3 and forms an edge with B4. Then in the next round, as B3 is the only one free, it goes on to propose to A3. But since it has already an edge and it prefers its present edge over an edge with B3, so it rejects. Then B3 goes on to propose to A1. It again gets rejected. Then it goes on to A2. It gets accepted. And that's your final perfect stable match. So there's some monotonicity here. The group that proposes always moves down their preference list, while the receivers, or rather the person being proposed to, their tentative partners only improve over time. Now, to show that the Gale-Shapley algorithm always gives a stable matching, assume this, that the final matching has a blocking pair. In that case, it can't be stable. So that is to say there exists some X that prefers Y to its final partner. But in that case, X must have proposed to Y earlier. So when Y rejected X or later dropped X, it shows someone it preferred to X. So the condition for a blocking pair was X preferred Y over its current partner. So this Y is YI and it preferred it over its current partner YJ. And YI must also prefer X over its current partner. Yeah, let's just see. Is its current partner. But here, if X preferred YI over its current partner YJ, then X would have proposed to YI before YJ, and YI must have rejected X for it to go down its preference list to YJ. So, so what happens is that why I can only reject X if the edge it had was already better for it, or maybe it formed an edge tentatively with X and then it found a better proposal, so it broke off that edge and then formed a new edge. So this condition, while might hold true, this condition cannot hold true. So thus Y cannot prefer X to its final partner. And this is a contradiction that we cannot get such a blocking pair. And thus can see that the Gale-Shapley algorithm always gives a stable matching. Well, as a conclusion, with equal size sets and complete preference list, Gale-Shapley produces a stable perfect matching. If you do not have a complete preference list, or if you do not have equal size sets, then Gale-Shapley does not work. But now, people might complain that in this case, well, only one side of it was given, to act on its preferences. The other side, while they had preferences, they were never allowed to act on it. Or maybe never allowed to actively act on it. Because the proposers get somewhat of an upper hand in actively pursuing the receivers. So here comes a concept called an arborescence. Arborescence takes a deviation from Gale-Shapley. I mean, it's also more relevant in cases of a democracy rather than a marriage, but I'll come to that. So what arborescence, okay, in case of an arborescence, you first the setting, you have a directed graph and a vertex R, which is a root, that is, it has no incoming edges. Now what in this case it does is that it has preferences of the edges that come in. Every vertex ranks all of them. And after that, what it's allowed to do is it's given a chance to vote whether it likes its present edges coming in, or if it has another option, with which one does it like better of the two. Maybe an example will make it more clear. So this will be our example graph for arborescences. Take a good look at it. I'll give you a minute and then we can move.
So what are we exactly calling arborescence? Is this topic? What?
So this concept is called arborescences. I have not defined what an arborescence is yet. I'll come to that.
Okay.
It's just a setting that we are working with for now. Okay. So now for the definition of an arborescence. And R arborescence is a directed tree rooted at R such that every V belongs to V has exactly one incoming edge. Okay, is the definition clear?
Rooted at R means?
Rooted at R means basically, so as the root was defined here, a root is a vertex which has no incoming edge.
Okay.
So I mean, you'll see that R is the only vertex that has no incoming edge. Every other vertex has an incoming edge. So yeah, and R arborescence is rooted at R, and every vertex V has exactly one incoming edge. Is the definition clear?
Yeah. And so we actually discussed two sets, having two sets.
Sorry, could you repeat? I could not get you.
Like, why don't we have two sets now? Like,
oh, because the thing is, well, you can have two sets. I'll come to that. I mean, see, since I said that this arborescence concept is rather less preferential in a marriage and more preferential in something called, I mean, you all know this. This is more preferential in democracy. And democracy, in that you do not make pairs as such. You just choose the better option always. So Okay, my idea to convince you through arborescences is a well, a common question that arises in Gale-Shapley algorithm is that one side is allowed to propose, the other is not. So one person can actively weigh out its option, but the other side, while having preferences, cannot do that. So you can complain that okay, maybe it's stable, but maybe everyone is not happy with the arrangement. So arborescences, well, in democracy, a concept that's very important is how popular is one. Like, for example, if elections are going on and there are two parties running for the elections, let's say party A and party B. So the more popular a party, the more the chances that the more people will vote for it. And the one getting the most number of votes essentially wins. So, and that is kind of the question that this boils down to, because, well, the question that if the matching is stable, that's fine with us. But what if not the most people are happy with it? So if the most people are not happy with it, maybe there exists some other stable matching with which most people are happy. That is stable matching that is much more popular than the current stable matching that we have. Does that make sense?
Yes.
Someone asked what a directed graph is. Oh, wait. Maybe I should have defined it. Let me go to the last slide. I have more space. Yeah, so okay, for starters, what an undirected graph is basically the graph has many vertices, it has edges between them, but there is no particular order to it. Like, for example, if you know what a path is, like, for example, if you are trying to go from V1 to V3, you can take this path that V1 to V2, then V2 to V3. And for going from V3 to make this easier, let's do this. Yeah. And for going from V3 to V2, you can again traverse back this exact path. So for a directed graph, the distance between V1 and V3 has to be equal to the distance between V3 and V1. The distance being the number of edges that it covers in between. But in case of a directed graph, all of these edges have a direction. That is clear, where in an undirected case, you could have gone from V1 to V2 and back from V2 to V1. In a directed case, you can only go from V1 to V4, but you cannot go from V4 to V1 since this edge now has a direction. Like, for example, if I define the directions as such. Yeah. So now the distance from V3 to V1 can be taken as, the path is V3, V2, and then V1. So the distance is 2. But then coming from V1 to coming from V1 to V3, you can't take this path again. Like, you can't go from V1 to V2, then V2 to V3, because there's no edge taking you in that direction. Rather, the only way that V1 can take is to V4, and well, then V5 and then V3. So the distance between V1 and V3 is now 3. So these two might not be equal in the directed case. So a directed graph is basically an undirected graph where every edge has been assigned a direction. Swayansu, is that clear? Am I pronouncing your name correct?
Yes, sir.
Okay. Yeah, so the basic definition of arborescence, I hope it's clear by now. Yeah, so in this preference order, like, okay, so the preference is like the preference of each vertex is on the incoming edges. Like for A, let's say the preference is this is the third preferred one, this is the most preferred one, this is the second most preferred one. It's not the outgoing edges that it has a preference on, it has a preference on the incoming edges. So, like, in this case, this is an arborescence where A gets his third most, like the worst edge that it can ever get. B gets its first preference. C gets his second best preference, and D also gets its best preference that it can get. Now, coming to the concept of popularity. So, for getting to popularity, we need to know how to compare to arborescences, right? So, let's say you have these two arborescences. The solid lines ones, we call them the arborescence A, and the dotted line ones, we call them the arborescence A dash. So to compare them, we allow each vertex to cast a vote for the one where it receives the better incoming edge. That is the one that it prefers most. So, well, in this case, A got it, like in case A, in case B, okay. So, case A dash, A, B, C. Yeah. So in the case of A, the small a got its third preferred edge, whereas in A dash, it got its second preferred edge. So the vote of A clearly goes to A dash. For B, it got... Oh, yeah. Yeah, so in B, okay, just mind you that this A to B, there's just one edge from A to B. And just for the clarity of it, I had drawn a dotted edge and the solid edge. But yeah, so for B, the edge remains the same. So it does not bother B much. So it can sway any side, A or A dash. So we take that to be a neutral vote. Let's say that's a nota vote. For C, which edge did it receive? Yeah, in the solid case, it received the second most preferred edge. In the dotted case, it got the most preferred edge that it had. And in case of D, yeah, in the solid case, it got its favorite edge, whereas in the dotted case, it got its least favorite edge. So now, after the votes are cast, you see that A dash gets 2 votes, A gets 1 vote, and there's one guy who does not prefer one over the other, so he gives a nota vote. So clearly, A dash is more popular than A in this case, as it gets more votes, like more people prefer it over the other. And that's, yeah, the exact same thing written out here. So now coming to the concept of popularity. So arborescence A is popular. If there is no arborescence, yeah.
So isn't it possible that two graphs are equally popular?
Yeah, two graphs can be equally popular. But
answer, yes.
Yeah, no, go on.
So in the graph that you made, can you show that slide, please? The chart that you made. Yes, here. So we can define a sum, like for example, these ranks. We can sum all of these and can make a, you can say, a marking based system, and the one who gets the less total marks, like for A prime, it is 2 plus 1 plus 1 plus 3, that is 7, and for A it is also 7. So according to that, it shows that A and A dash are equally popular, because
Yeah. Yeah, so that problem with the sum is in this case it shows they're equally popular, but that is mostly skewed by D, because, well, you know, A and C get a slightly better choice, but D's preference goes down drastically. So as I said, this is more preferable in a democracy. So it does not matter whether everyone gets a slightly better or slightly worse choice. What matters is if the majority likes it or not. So in this case, A and C form the majority. They like it. So their choice takes precedence over A. Now, if you summed it up, yes, it's more or less the same because, I mean, in choosing A dash, while the state of A and C improves, the state of D like goes down drastically. But again, it's in sense of a democracy, so the majority takes precedence.
Yeah, got it.
Yeah. Okay. So yeah, in case of popularity, s- so yeah, equal number of people can vote for A and like A and A dash can get equal number of votes. In that case, that's a tie. But then you define popular arborescences, so you choose one of them, and then you say that this arborescence. Oh, yeah. So maybe I'll go on with this A dash. So you choose A dash, and then you say that A dash is popular if there is no other arborescence that is more popular than this. That is the most number of vertices prefer their edges in this particular arborescence. Like for example, if there came some, yeah, if I could come up with some A double dash in which it had greater number of votes than A dash, then I will say that A double dash is more popular than A dash. Or even if A double dash is the same number of votes as A dash, then A dash remains my popular arborescence. And I say that, okay, A dash is my popular arborescence because there's no other like arborescence that has strictly greater number of votes than A dash does. So yeah, that's how you define the popularity. Like you call an arborescence popular if there's no other arborescence that is more popular than. And okay, keep in mind this notation. So this is used to mean that A dash is more popular than A. The thing is that in case of stable marriages, stability had was always ensured. But in case of popular arborescence, a popular arborescence need not always exist. Like a unique popular arborescence need not always exist. So check in this case. Compare A and A dash. A and C prefer A dash over A. D prefers A over A dash. And B, it's one of the same for it. So A dash is more popular than A. In a comparison between A dash and A double dash, D prefers A double dash over A dash. B prefers A dash over A double dash. And C remains unbothered. So A double dash is as popular as so A double dash is more popular than A dash. Now we again compare A double dash and A. Well, in this case, B and D prefer A over A double dash, and A and C prefer A double dash over A. So A is as popular as A double dash. But then, in saying that, you get two popular arborescences, A and A double dash. So you get no popular arborescence, and A double dash being as popular as A, and A dash being more popular than A. It has somewhat of an implication of this, that since these two are as popular as the other, the ones more popular than this must also be more popular than this. So you do not have a consensus that one of them is more popular than all of the others. So you end up with a conclusion that popular arborescence does not exist. So this is, well, I said it's useful in democracy, but it's more useful in something that we call a liquid democracy. So a liquid democracy is a concept where each voter may go to vote directly, as we normally do in our elections, or they might delegate their vote to another voter they trust. Like, for example, there's this person A, I go to him and I say, okay, you know what? You can just go ahead and give my vote for this election. I delegate my vote to you. And that's what this arborescence can very well model. So, with the condition that R gives the direct vote, the edges being the ones being delegated to, and the ranks are the trust values of the ones that delegate these. So, delegations will always be transitive. That is, if U delegates his vote to V and V delegates his vote to W, then that means that both the votes of U and V are given through W. Delegation cycles are forbidden. That is, you can't have U giving its vote delegation to V, V delegating it to W, and W delegating it to U. Then you never have a vote from these three people. So the delegation tree is naturally an arborescence rooted at direct representatives. And popularity asks whether a majority prefers another delegation tree. Yeah, so till now, is the arborescence idea clear? Or the popularity in arborescence idea clear?
Yes, sir, it's clear.
Okay. Then now let me move on to popular matchings. Well, as I had stable matchings and stable marriages or stable matchings. Now I introduce the idea of popular matchings. Now I come to the conclusion of it all. Like the popularity in case of those stable marriages. The question was, okay, the marriages are stable. We're fine with that. But is the marriage popular? Like, do the participants participating in the marriage, in the stable marriage, are all of them happy with it, or do they prefer a marriage that more another stable marriage that's more popular than it? Do we have such a stable marriage rather?
So, what was the definition of stable marriage exactly?
So stable marriage is just so stable marriage is just what Gale-Shapley does. It's basically it gives a perfect matching and then ensures that there's no such blocking pair where one like in two pairs, one of them from each prefers the partner of the other over their own.
Okay, got it.
So the question is that a stable marriage is, all right, stable, but is it the most popular? Are the people happy with it, or there is another alternative that makes them happier? And that's where this popular matching concept comes in. That's what Gärdenfors did in 1975. He introduced popularity as a majority vote notion for matchings. So basically, what it does is for two given matchings, let's say M and N, each vertex votes for the matching, giving it the better part. Same if they have the same partner in both the matchings, that means they cannot vote. And being unmatched is considered worse than any acceptable partner. And popular matching does one thing better than stable matching that I should accept is that stable matching is bound or rather hinged on the fact that the sets that we have, both of their cardinality must be the same. Popular matching does not bother itself with that. It lets you rank all of the candidates and ranks being unmatched at the very end. So every candidate preference here, and then all of those is much better than remaining unmatched. So unmatched is also an option in popular matching, and that gives it a slight edge over stable matching. But then, while we are considering stable matching as this was our condition for the starters, we will stick to this for now. So quick notation, there's phi of m comma n, where m and n are two matchings. This represents the number of vertices that prefer the matching m over the matching n. A matching m is popular if phi of m comma n is greater than equals phi of n comma m for every matching n. So this is the exact theorem by Gärdenfors. It is that in the stable marriage setting, every stable matching is popular. That is to say that the stable matching that Gale-Shapley gives when we have complete preference lists and when we have equal cardinality of both the groups, that is indeed the popular matching. Question is why this is plausible. Well, if another matching, say n, defeated a stable matching m, then a majority of vertices would improve by switching from m to n. And if that happens, it's the other way around. A stable matching implies a popular matching, but a popular matching does not imply a stable matching, rather. Because, as I said, that stable matching is hinged on this factor, which popular matching is not dependent on. So if I can get a stable matching, I can say that this is also a popular matching. But a popular matching does not necessarily mean a stable matching.
Yes, so this is by definition.
Sorry?
So this can be inferred by a definition, can't it?
Yeah. Because popularity is not dependent on this fact.
And
Yeah,
so
so
the fact that table is popular. This fact is through definition.
sorry?
And so the fact that every stable will always be a popular combination. So this is through definition.
That is not like that's what I'm trying to give you an intuition of how it works. So that is the thing, that if let's say the stable matching was not the popular matching, so there must exist some matching n. So let's say your present stable matching is m. There exists some stable matching n, or some matching n rather, that is more popular than m. So if another matching n defeated a stable matching m, then a majority of vertices would improve by switching from m to n. But such an improvement can be traced through alternating paths or cycle and yields a blocking pair for m contradicting stability. Like, for example, as I said, in popularity case, we also rank the unmatched condition to be the worst thing possible for you. So let's say there was a let's say there was a condition where some n was preferred over some m. Then in so think of just two pairs, x1, y1, x2, y2. Assume they are matched. So x1 prefers y2 over y1. Yeah, let's take x1 prefers y1 over y2. And y2 prefers x1 over x2. Now, if you switch these, like you match them in this order, then you lose y2's vote, but you gain x1's vote. Uh, Correct. So in that case, the popularity remains the same in both the matchings. So there cannot be a matching that's more popular. As popular, yes, but it's not more popular. Now, let's say the number of votes strictly increased from M to N and M was a stable matching. That can only happen if X1 preferred Y1 over Y2, and I should choose a different color maybe. Yeah, so the red are the ones if we change. So let's say X1 preferred Y1 over Y2 and Y2 preferred X2 over X1. Only in this case does the number of votes increase. So uh, now we break off those edges and then we match X2 to Y2 and X1 to Y1. There's a strict increase of 2 votes from M. But then this is exactly the definition of a blocking pair. And we earlier concluded that Gale-Shapley can always will give you a stable matching and does no blocking pairs. So whatever stable matching that Gale-Shapley gives you a popular matching. There can be other popular matchings, but this one is as popular as it gets. I mean, there's no matching that's more popular than this, like strictly more popular than this. Well, in Gale-Shapley, many people, yeah, as I was saying, many people try doing these kind of examples, students and projects, let's say residents and houses. But then in those cases, there's one slight problem there. The Gale-Shapley algorithm assumes that everyone in that list, I mean, both the groups have their preferences, but houses don't have preferences, projects don't have preferences. The students do, the humans do, the residents do. So in that case, what comes in is again this popular matching, or rather popular matching in one-sided preferences in bipartite graphs. So let's look at house allocation model. Like you can look at project allocations to students, but we'll look at this house allocation thing. So take G to be a bipartite graph, take the vertices in A as agents or the residents, take the vertices in B to be houses. Now, each agent A belongs to A strictly ranks its acceptable houses in its neighborhood. Houses are indifferent and they have no preference. For a matching M, write MA for the house matched to A, or so if it's matched, then this. If it's unmatched, then this. And then again, the popular matching condition holds that a house being unassigned to anyone is the least preferable option that we have. So M is popular if no matching N gets more agent votes than M. So in popular, okay. So one major differences that you will see between arborescence and matching in case of their popularity is arborescence always wants in case of popularity arborescence for which it is strictly more popular than each and every other arborescence. While matching, popularity is hinged on the fact that a matching has popularity greater than or equals to every other matching. So now, let's say each of these agents have a preference, say like this. Okay, the preference here is a bit jumbled up. Maybe you can use this chart below. Yeah, so every agent has the same ranking, that it prefers B0 over B1 and B1 over B2. So now consider this case. We compare the green matching with the blue matching. So A0 gets B0, A1 gets B1, A2 gets B2. In the blue case, and in the green case, A0 gets B2, A1 gets B0, and A2 gets B1. Now the comparison. Well, in the blue case, B0 got its rank 1 option, and in the green case, it got its rank 3 option. So it would vote for blue. In the for A1, in the blue case, it got a rank 2 option, and in green case, it got a rank 1 option. So it would vote for green. For A2, in blue, it got a rank 3 option, and in green, it got a rank 2 option. So it would again vote for green. So we'd say that green is strictly more popular than blue. Next, we compare the red versus the green. Even in this case, you would see that two of them prefer the red over the green, and one of them just preferred the green over the red. So red is a more popular matching than green. Now, the last comparison that must come is the red with the blue. But even in that case, two people prefer blue over red, and one person prefers the red over the blue. So blue is more popular than red. So what you essentially get is that blue is more popular than red, which is more popular than green, which is more popular than blue. And this goes on in a cycle. So you can never reach a popular matching. And mind you, in case where both the sides had preferences, you would always reach at a popular matching, which would be your stable matching. Given both the sides had same cardinality. But if just one side has a preference, the other side has no preference at all, then there can be cases where there comes no popular matching and you go on in cycles like this. So yeah, in each of those, one of them loses to the other in a 2-for-1 vote. And thus you can never get a popular matching in that particular example. So these are three very important ideas that we kind of try to discuss is stable matching, popular arborescences, and popular matchings. And each of them cater to a certain kind of problem. While this caters to a marriage kind of problem, this caters to a household registry kind of problem. This caters to a democracy kind of problem. Each one has an edge over the other. So they each find their application in different kinds of stuff. Like, for example, here in both these cases, you allow everyone to have a preference. But in this case, you allow only one side of the party to have a preference. The other side does not have a preference. In this case, you are hinged on the fact that the cardinality are equal. In these two cases, you do not bother about that. In this case, there is only one active pursuer. In this case, everyone who has a preference pursues. And in this case, you allow each of the person with a preference to vote and decide which one they prefer more. In this case, there's no voting happening, but well, you still end up with a popular matching, so you cannot complain. So yeah, these were some of the ideas that I just wanted to walk you through, because well, matching arborescences, these are kind of concepts that are still very much active in research even today, both in mathematics and in theoretical computer science. And these are some references that you can look at. These are papers. And this is a book. It's a very interesting book. if any one of you have prepared for exams like this ZCO, ZIO, INOI kind of stuff, then maybe you would have at least heard of this book. This gives quite a good idea of the Gale-Shapley algorithm, as well as other kinds of algorithms as well, and algorithmic techniques. And the other ones, well, they are some of the places that I borrowed these ideas from. This is the exact paper where Hall first mentioned the Hall's marriage theorem. This is Gärdenfors' proof for why the stable matching is a popular matching. This is the paper where Gale-Shapley gave the algorithm, and this is a paper. Well, interestingly, this woman is the only Indian here. She's a professor at TIFR currently, and this is a very interesting paper on popular matchings, and she also has some papers on arborescences. You can have a look at the papers or have a look at the books, and well, I'll send you the slides once the camp is over. And that's all. So if you have any question, please feel free to ask. So how agents? Wait, sorry, I did not see the questions. Then how agents chooses as blue, green, red matches? Well, the thing is, since this is a very theoretical model, it's not like you don't apply all theoretical models to practicality. So agents, the popularity vote keeps on changing and changing, and it does not just depend, like in real world, it does not just depend on which is more popular, who wants which. It hinges on a large variety of factors. This is a theoretical model, and well, that's a counterexample that shows that popular matchings well might not exist in all cases. Yeah, though these things have some practical examples as such, they well do not always imply that these things will always work in practicality, because what researchers do particularly is they take a question in all of its generality, they put many assumptions on it, well, discard of other factors, isolate the problem completely, and then try to solve it. And then slowly and gradually they move on to the general setting. So, yeah, these are theoretical models, and they're still not caught up to the real world. Yeah, well, that's all. Maybe I'll stop the presentation.
So thanks a lot, sir.
Thanks, sir. Vinam, congratulations.
Yeah, you too.